Hello everyone. Here we present our work entitled Vision Transformer Adapters for Generalizable Multitask Learning. Our project page with all the necessary details can be found on the QR code here. The problem we address over here is that multitask affinities learned by existing MTL frameworks are not transferable to unseen tasks and not generalizable to novel domains, restricting their reusability. To solve this issue, we introduce Vision Transformer Adapters for Generalizable Multitask Learning, an automated framework that can learn transferable and generalizable task affinities, which can adapt to new tasks or domains in a parameter-efficient manner. Our model does not need retraining or fine-tuning, and it can achieve multitask learning, zero-shot task transfer learning, unsupervised domain adaptation, as well as domain generalization without fine-tuning, provided that the domains are not extremely disparate. Following the swim transformer architecture, this method encodes the images using the different swim stages, which is frozen but initialized with pre-trained ImageNet 22K model weights. The training mainly takes in the vision adapters shown in purple, where different mechanisms are at play. One such mechanism being truer, which is a gradient similarity method to calculate task affinities. It is dubbed the task representation optimization algorithm. I will explain the vision adapters in more detail, but before that, let me give you an overview. Once the task representations are learned in the encoder, they are passed down the decoders and through the respective task heads to achieve the predictions. Now the main contribution of this work are the adapters in purple, which use truer. So what is truer? Truer is the task representation optimization algorithm, where we find the gradient-based task similarities between the tasks of segmentation, depth, normal, and edges. In essence, it calculates the cosine similarity between all the tasks and does an analytical weight update to obtain this task affinity matrix. For example, we get the affinities of segmentation with segmentation, segmentation with depth, segmentation with normal, and segmentation with edges. This task affinity for a given task of segmentation is weighted averaged with the task embeddings that are learned by the overall network, and then scaled and shifted via a feature-wise linear modulation operation. We use a learnable matrix A that is randomly initialized and scaled and shifted with the feature-wise linear modulation parameters gamma and beta. We get the scaled representation, which we pad with empty cells to match the spatial resolution of the normal attention matrix, the QKT matrix, coming from the image. This transformation operation is done to match the spatial resolution of the reddish matrix that gives the task affinities with the bluish matrix that is the normal attention matrix. This is what happens within our introduced task-adapted attention module. In more detail, we combine the two matrices in our introduced task-adapted attention module and pass the sum through a softmax operation, which is then followed by multiplying the value to get the single head attention output. This process is repeated m times for multiple heads, and we get the task-adapted attention at the end of it. If we visualize our task-adapted attention module, we see its effect on an example image, where the regular self-attention is not able to attend to the feature representations specific to a given task, simply because it has no notion of task representations beyond just the image features. In contrast, our task-adapted attention mechanism leverages the task affinities as well as representations from truer and combines them with the image feature seen in blue. And this gives us the task-specific attention as such seen over here in the form of semantic segmentation TAA. Similarly, this is the depth TAA. We will show that this task-adapted attention ultimately gives better predictions on the respective tasks. Building upon the task-adapted attention, we enter the purple-colored Vision Transformer Adapter module that uses the task-adapted attention to encode task-specific representations. The layer norm normalizes across all features, which has been seen to be more stable. We then pass the representations through a feed-forward network and use its output as well as its activations to scale the different tasks using a task-scaled normalization. This task-scale normalization matches the scales of the different tasks, which are known to be different in multitask literature. Finally, we use a bottleneck with a feed-forward down, non-linearity, and feed-forward up projection, reducing the number of parameters significantly. For the subsequent layers, we use a skip connection to allow the task-specific information to flow from preceding to succeeding layers. Qualitatively, if we focus within the yellow circled areas, our adapters segment the flower, the vase, and the table better than the baseline methods. We see the same performance of our adapters for the depth task. Further, for surface normals, the adapters outperform the baselines. And this trend is seen for edges as well. Our adapters also generalize the learned task affinities to zero-shot task transfer, where surface normal are zero-shot task. We see that the building door and the street light is better estimated for the zero-shot normal task using our adapters compared to the baselines. For the UTA setting, we apply domain discriminators at the output levels of the task heads to not change the network architecture. Here the source labels are present, but the target annotations are not available. For Cynthia-to Cityscapes, we see that our UTA method, unsupervised domain adaptation method, outperforms in segmentation by segmenting the car pixels accurately. For depth, the adapter UTA estimates the car and building depth more accurately than the baselines. For the domain generalization method, we do not need to fine-tune our trained multitask models. All we need is a target domain not too dissimilar to the source domain. For example, we use our trained multitasking models on MS-COCO on a common dataset. Let's see examples for segmentation and depth. In the top row, our adapters are the only method able to segment the plate where all the baseline methods fail. Moreover, for depth, our adapters predict the left hand of the character better than the baseline methods. Another example from DCM Comics shows that our adapters segment and predict the depth of the airplane more accurately compared to the baseline methods. Note that comics are very abstract and also disparate to a real-world photographic domain. We thus had to employ a style transfer mechanism to transfer the style of these comic images to that of the real world. For more results and quantitative evaluation, we defer the viewer to our project page. In summary, our work consists of the following 4 contributions. We find the task affinities across a set of tasks which are seen to be transferable to other tasks and generalizable to novel domains. We then combine these generalizable task affinities and their representations with image-based attention to get the task-adapted attention, which attends to the image features specific to the tasks. We bring all these together in a parameter-efficient vision transformer adapter framework. We ultimately use our adapters across 4 settings, namely multitask learning, zero-shot task transfer, unsupervised domain adaptation, and domain generalization. This work was supported by the Synergia grant from the Swiss National Science Foundation. And that concludes my presentation. Thank you for your attention.